In a recent article from Nature, scientists finally were able to test the strength of nanotubes, which is amazing news from the depths of the nanotechnology realm. Nevertheless, it looks like space elevators will remain in the land of science fiction a bit longer. But not everything is bad news. Hello everyone, Subject Zero here. It is the 1970s, and Arthur C. Clarke is stuck in his room thinking about the future. More like how to make his space novel cooler, but anyway, at some point he decides to use the idea of space elevator. In his novel Fountains of Paradise, he describes a future civilization with a really advanced system of a super strong cable that could be lowered into Earth and used to move objects up and down. This was the book that popularized the idea, and space elevators became a thing to the scientific community. But for many years, it was just that, a science fiction piece and nothing else. It was only in 1993 that many science nerds started to taste the fact that maybe they could actually bring this science fiction idea to life, with the discovery of nanotubes, a material that would revolutionize everything from that moment on. Or so they thought, because it's 2019 and they can't get the thing out of the lab. So, in his novel, which is depicted during the 22nd century, he described this system with a megastructure built on Earth and linked through with a cable to a satellite in a geostationary orbit. All of this happens at a distance of 35,786 kilometers? What? That's a really long cable. Who even thought of this? Who even thinks this is possible? Like 35,000 kilometers, man. Are you nuts? You must be crazy or... So, if we ignore most of the problems of building a space elevator, like the cable, and also most of the problems that Earth's atmosphere poses to this idea, like atmospheric turbulence, Coriolis forces, among many others, if we just ignore all of that and use some quick physics, complex mathematics, and the magic of the interwebs so we can skip all of the extremely complex calculation crap and go straight for the answer, we would need a cable that can handle at least 63 gigapascals. Historically, the idea was to build a space elevator from ground to space, but it quickly faded away as it was too unrealistic since there were no known materials that could withstand its own weight due to the massive structure. Years later, the best concept came from a Russian engineer, Yuri Artsutanov. Yuri suggested using a geostationary satellite that would lower the cable towards Earth and at the same time a counterweight to keep the satellite on the same level. At the end of the day, the problem with space elevators relies mostly on material strength, and that is why nanotubes became so important after its discovery. Because its early estimates put this material at some absurd level of strength, or to be more precise, 300 gigapascal. Nevertheless, the pursuit towards cheapest way to get things to space is what keeps this concept alive. For instance, even with SpaceX's recent advances making travel to space much cheaper, you still have to pay around $1,400 per kilogram, which is much better than just a few years ago when the cost was around $20,000 per kilogram. Space elevators would take that cost further down to about $220 per kilogram, which in paper looks really good, but reality tells a different story. Both transportation systems have their pros and cons, but the main argument against space elevators, aside from all its problems, is that a spaceship can travel at higher speeds, or about 26,600 kilometers an hour. It takes a little more than an hour to make that distance, while the elevator would take days. And at the end of the day, it's a bit of a trade-off. You can either go cheap or fast. But judging by how things are getting better on SpaceX side, the cost will most likely continue to fall. If prices per launch drop to about $600 per kilogram, then there will be little to no incentive at all for space elevators. And that's not the only bad news. Nanotubes, the one material that was the hope for space elevator enthusiasts, it's not cooperating either. So it turns out that nanotube strength has everything to do with its structural atomic configuration. In a recent article from Nature, a team led by Akira Takakura sort of confirmed one of the problems with the structure of nanotubes and why scientists weren't able to produce nanotube structures that reached the max theorized strength. Like I mentioned before, Good news for ongoing research, but very bad news for space elevators. And this is not the first time the nanotube strength has been pushed back. In its earlier years, it was thought that the strength was close to 300 gigapascals, but a few years later it was lowered to in between 100 and 200 GPa. These numbers are nothing more than a theory based on atomic bond strength to which they extrapolated and got to 300 GPa at first. Over the years, scientific equipment got more precise, eventually leading to a revision of earlier predictions. Nevertheless, anything in the GPa level is still really strong. A quick comparison with other materials show how much bigger the strength of nanotubes is in comparison. Notice that even the lowest strength-to-weight ratio yielded by lab tests is much higher. Nanotube weakest configuration is still 10 times stronger than Kevlar. But this problem of extreme strength variation can be easily attributed to the methods used to synthesize the tubes. This is a common problem in nanotechnology, where you can only really go for either one of the two things, quality or quantity, something that I have addressed previously in many of my videos. Nanotubes are nothing more than cylindrically rolled graphene sheets. Yes, guys, I do read your comments. For a few years now, they have been theorized to be an outstanding material in terms of strength-to-weight ratio, and it is because of that that the whole idea of space elevators could actually come true in the near future. If only they could prove that nanotubes were as strong as they were thought out to be. This is important because the strength necessary to get anything close to a space elevator going, like I mentioned before, needs to be at least 63 GPa. But what is it that they figured it out? Well, it turns out that there are 3 configurations that you can make nanotubes in, and that is what they tested. All of the 3 configurations yields completely different strength values, which is okay, but the problem is that in some cases the strength is well below the 63 GPa, while other times it barely passes that. However, it never even gets close to the predicted values of 100 to 200 GPa. This is a problem attributed to the production techniques used. For instance, in this experiment, they used a method of chemical vapor deposition developed back in 2002, using low temperature with alcohol as the carbon source. Keep in mind that there are many types of CVD technology, and this is just one of them. The technique discussed here was developed with a low cost and low temperature production in mind, not high quality. Nonetheless, with recent advancements, it can yield high quality tubes with only a few tweaks. To synthesize the tubes, they used iron acetate and cobalt acetate dissolved in ethanol, which are the metal catalysts for the reaction. They are then introduced into a furnace that heats everything up to a temperature at max 600 degrees Celsius, and the reaction takes place with alcohol vapor being injected into the chamber. This technique is way more complex than I'm describing here, so if you're interested in making nanotubes yourself or would like to just read the paper for fun, the link is available in the description below. They analyzed the tubes using scanning electron microscopes and transmission electron microscopes to verify the structure of the nanotubes created. It is at this moment that they are able to identify the structural configuration of the tubes. One point I must stress is that no scientist knows for sure why there is so much variability in terms of tensile strength, but apparently the arrangement of the structure may play a role. Worse yet, up till now, there were no tests conducted about this, which shocked me at first and makes everything indeed science fiction. To highlight what I'm talking about, we need to understand how hexagon patterns can be shifted around to create alternative structural patterns. Let's take a look at a graphene sheet. If we roll it the way it is showing on the screen, you will get the most famous nanotube pattern that most likely you have seen everywhere. But if you change the angle of the hexagons just so slightly, magic happens. Just by changing the angle 15 to 30 degrees, you can completely change the entire structure and strength of the nanotube. Keep this in mind because it will become important later. Once synthesized, they test each individual nanotube strength by using a micro-electromechanical system which basically pulls the tubes apart while measuring its strength. And what they found was staggering. They managed to test 16 variations of structures, like the ones I defined earlier, and showed that the strength is deeply dependent on the angle and diameter of the tube. These tests yielded results ranging in between 22 and 66 GPa, which can be attributed to problems within the structure of the tubes. The weakest tubes were in the diameter range of 1.5 to 2 nanometers plus, while the armchair configuration yielded the highest strength of more than or equal to 70 GPa. Kairos showed the lowest strength or less than 25 GPa. Now keep in mind that these tubes were not perfect, hence why we won't see the strength near 100 GPa until they manage to make defect-free tubes. The ultimate conclusion is that the strength of nanotubes is a linear relationship in between the chiral angle, diameter of the tube, and size of the defect. Basically, what this means is that for each angle there is a maximum stress that the tube can take. A more armchair-like configuration should yield the strongest configuration. However, if there are any defects on the tube, it will have an impact on the structure that is dependent on the diameter. The smaller the diameter, the more any defect impacts the overall strength. The opposite is also true. The bigger, the less. But if the diameter gets too big, then the structure also loses strength. So the sweet spot we could say for now is that the armchair configuration with a diameter less than 1.5 nanometer is optimal. Ultimately, what this means is that there is an optimal structural configuration to be targeted and an intrinsic need to further ameliorate current methods of production to achieve this, or else we will never have space elevators. But then again, SpaceX is about to send space elevators back to the science fiction realm anyway, if they keep up with the good work that they're doing. Alright folks, that's it, we're done here.